Good morning to all of you. Today, I Satyam Kumar Misra is going to share my knowledge on the topic Hardwired Control Unit in Computer Organization and Architecture. This presentation explains the structure, operation, and strength and trade-off of the hardwired control unit, the fixed logic engine that directs CPU at clock cycle speed, clear diagrams, step-by-step explanation, and comparative context help you understand why designers choose hardware control for high-performance processors. Basically, we are going to learn about advantages, disadvantages, and what the thing is hardwired control unit and its difference from the microprogrammed control unit and how both of these works and extra. First, we will try to learn about the topic what is a control unit. The control unit or CU directs the CPU operations by generating and sequencing control signals that coordinate the data path, memory access, and peripheral instructions. It interprets the concurrent instruction and orchestras the fetch, decode, execute cycle. The broad implementation style exists. First, we'll learn about hardware control unit. Its control realize that dedicated combinational and sequential logics, which can be gates, decoder, flip-flops, etc. Fast, and its benefit is that it is fast and cycle accurate. It behaves as finite state machine. Basically, its advantages are that it has low latency, but the problem in it is that it is too complex and has less flexibility. Now moving to microprogram control unit. Its control produces by sequences of micro instructions stored in control memory, easier to modify and extend, but introduces micro instruction fetch overhead. Means in this one extra step will be added, so our latency will get, you can say, to a little high from the hardwired control unit, but we'll get a high flexibility. We can choose both of them as per our need, or we can use both of them, you can say, in parts. Now defining the hardwired control unit, its definitions. A hardwired control unit uses fixed logic circuits to translate instructions field flag conditions into control signals. It typically implements a finite state machine whose state transition occur each clock cycle with combinational logic mapping the current state and instruction bits to outputs. First we will talk about inputs. In input, we will give an opcode bit from the instruction register, status flag, external interrupt. Means first I will tell you about the block instruction register. It is the block that or you can say a part which store all the instruction which will be done in future. It stores everything, like we stores numbers in an array. It is just an example. State, step counter and state register track the micro steps. And now we'll go to outputs. Control lines that enable or disable multiplexers, load signals, ALU operations, memory read or write, and bus drivers. Because logic is hardwired, the timing is deterministic and optimized for minimal latency. Now moving to next page. Architecture overview and block diagram. first we'll talk about core components and its responsibilities. The first component is instruction register. It holds the current machine instruction bit in form of opcode, operands, and addressing mode. The second component of our architecture is instruction decoder. Converts opcode bits into internal codes used by control logic, extract fields for addressing and operation selections. The next element is step counter, or you can say state register. Sequences the FSM macro step from T1 to T2 to Tn, etc., determining the timing of control signal emission. Control signal generator. Combinational logic that map state plus decode opcode plus it flags it concrete control lines. Example: MAR load for loading this data, memread for reading the data, ALU opcode like plus minus, etc. Regwrite means for writing in registers. The final element is clock and external input. Clock drives state transition, interrupts, and status flags can alter sequencing or force special control sites. Now, at first I would like to tell you that instruction register, as I have told you earlier, that it is an element, or you can say a core component, that stores all the instructions which are being done or will be done in future. The second element is instruction decoder. It just decodes the signals coming from instruction register and make it in the form so that computer can understand what he has to done. The next element or component is step counter, or we can say the state register. It don't do much, you can say, but it has only one work: to determine the timing of how the signal will be emitted. The final element is the control signal generator. It generates the signal and sends it to the elements and tells them what to do. Now moving to next slide. How it works: step-by-step execution. Typically FSM driven instruction timing. Example with up to 5 microsteps. The first step is T1, fetch address. PC output means PC output to MAR means memory registers. Assert memread, increment PC if required. The next T2, memory read, data from memory placed on a bus into IR instruction bits become available to the decoder. Then decode and operand fetch. Decoder select ALU op and addressing modes. If needed, fetch operand from register file, execute ALU, perform operations, control lines, set to root data, select ALU functions, and handle branches. Write back and next PC. Result return to destination register or memory PC for next instruction. Step counter reset or advances to next instruction cycle. Basically there are 4 steps. T1, that is fetching the data. Second step is to read the data. Third step is to decode the data. What we have to done means decode the instruction, and final step is to execute. Means what what instruction we have got. Now we'll talk about the advantages of hardwired control unit. The first advantage is high speed. Dedicated combinational logic yield minimal propagation delay. Control signals are produced in fewer cycles compared to micro instruction fetch, ideal for low latency and high clock speed. The second advantage is deterministic timing. FSM sequencing produces predictable, tightly bounded control timing, beneficial for pipeline timing and real-time constraints. The third advantage is no control memory overhead. Eliminates the extra cycles required to read micro instruction from control ROM, reducing overall instruction latency and silicon area in some designing. Optimized for RISC. Suit simple orthogonal instruction sets with fixed format where logic can be aggressively optimized for control paths. Moving to the next slide. The disadvantages and practical challenges for the hardwired control unit. While fast hardwired control unit presents important trade-off that impact development cost, flexibility, and product life cycle. First problem is design complexity. As instruction set grows, variable formats and addressing modes, privilege of operations, the combination logics become large and error prone. The second disadvantage is limited flexibility. Any ISA change or new instruction requires hardware modification, respin or FPGA updates are costly and slow. The third disadvantage is testing and verification cost. Exhaustive verification of all state transition and timing path in laborious and expensive. Scalability. Implementing micro-architectural extensions, virtualization, complex exception handling is easier in microprogrammed designs. Designers often adopt approaches hardware control unit for logic for hot common paths and small microcode for programmable sequencers for exceptional or complex instructions. Now moving towards the differences between hardware and microprogrammed trade-offs. Microprogrammed control. In microprogram, control logic expressed as micro instructions in control memory. It is easier to modify, extend or patch since control stores updates. Slightly slower due to micro instruction fetch and sequencing. Useful for complex CISC feature and backward compatibility. Choosing between them depends on target performance, complexity of the ISA, need for the future extensibility, and cost time for hardware updates. Real world contexts and examples. RISC family. Modern ARM context, many embedded cores often use hardwired control to achieve high frequency and low latency. Traditional CISC design control microcoded x86 implementation relied on microprogramming to implement complex variable length instruction sets and facilitate compatibility layers. Contemporary CPU design sometimes mix approaches. Hardware micropath for control instruction and microcode for complex system levels operation, exception, complex string instruction and BIOS compatibility. Now the final conclusion and takeaways. Performance first. If you are moving towards the performance, hardware control units deliver the lowest latency for control signals generation, critical for high frequency, performance sensitive design. Second point is complexity versus flexibility. The faster paths come at the cost of flexibility and higher design text overhead. Microprogramming remain valuable where extensibility and compatibility matters. Modern design and modern practices. Modern architectures and apply hybrid strategies, hardwired for hot path and microcode firmware for complex control. Understanding both paradigms is essential for CPU design and architectural work. For architecture and design, mastering the hardwired control unit concept is foundational. It illuminates how instruction translates to moving towards the microprogrammed control unit. Yep. In computer organization and architecture. This presentation explains the microprogrammed control unit (MCU), what it is, how it works, its architecture and micro instruction format, and why it remains vital in modern computer design. Expect details, description, diagram of sequencing component, comparative analysis and hardwired control unit, and real world implication, all written to stand alone as a concise reference. Moving towards what it is, control unit, the brain behind CPU operations. The control unit orchestrates execution inside the CPU. It interprets machine instruction, generate control signals, and sequences operation across data path element, ALU register, buses, memory. There are two principal control strategies. First, hardware control implements control and fixed combinational and sequential logic. Its advantages are minimal instruction latency and high throughput. Its drawbacks are complex design for rich ISA, difficult to change and extend, means it is to reject, you can say. For microprogram control unit, implement control as micro instructions stored in control memory in microcode form. Its advantages are flexibility, easier maintenance, and drawbacks are fetch interpretation step adds latency. Microprogrammed unit act like a small firmware engine inside a CPU, mapping each machine instruction to a sequence of lower level micro operations. Hardwired versus microprogrammed, key differences. First, we'll talk about performance. In performance, hardwired is better. Hardwired typically yields lower control path latency. Microprogrammed adds an extra level microfetch, so it's comparatively slower per instruction. Flexibility. In flexibility, microprogrammed one is better. Microprogrammed unit can be patched or extended via control memory updates from ROM to flash to RAM. Hardwired units required hardware redesign for changes. For in complexity management, microcode simplifies implementing complex CISC instruction by decomposing them into reusable micro instruction. On the other hand, hardware requires intricate control logic to achieve the same. Use cases. Hardwired favored in high performance RISC cores. Microprogrammed is favored historically in CISC design and in any design requiring updatability and emulation. Control memory type influences system behavior. ROM for fixed microcode, writable control stores RAM and flashes, enable update and dynamic programming. Moving towards next slide. What is a microprogrammed control unit? The microprogrammed control unit generate precise control signals by executing micro instruction stores in control memory. Each micro instruction encode a control word, a vector that stimulates, drives multiple control line. Register enables ALU operations, memory read-write. A microprogram is a sequence of micro instructions that together implements one machine level instruction. In essence, microprogramming turns control logic into firmware, readable, editable, and modular. Control memory effectively designs the CPU behavior. Changing microcode can change instruction semantics, fix hardware bugs, or add new instruction without changing silicon. Now its architecture and key components. Microprogram control unit comprises several cooperation registers and buses. Key components are: first, instruction register. As we know about instruction register, the instruction registers holds at the fetch machine instruction the opcode and possible mode bit. Select the starting address for the corresponding microprogram. Basically, it stores all the instructions that are being done or will be done in future. And the second component is control memory, microcode store, non-volatile ROM or writable stores containing micro instructions. Each location hold a control word plus sequencing fields, address, condition, and condition bits. It basically means that microcode word store, that first we have the mode, then address, then conditions, etc, etc. The third thing is micro instruction register or MIR. Holds the currently executing micro instruction. It feeds directly drive path control line during the microcycle. The fourth component is microprogram counter or CMAR. How it works: CMAR or microprogram counter hold the address of the next micro instruction. Sequencing logic implements it, loads branching address based on micro instruction field and condition flags. Sequencing logic and mux, or you can say multiplexer and conditional logic selects between incremented address, branch target, or opcode derived entry points, flags, and external condition to determine conditional branches. Moving towards how it works: micro instruction sequencing. First step is fetch, second step is entry, third step is fetch micro, fourth is execute, and fifth is sequence. The design above summarize the typical sequence. Instruction fetch: the CPU fetches the machine instruction into IR or instruction register. Entry address: opcode or opcode plus mode maps to the microprogram start address. Load into CMAR. Microfetch: control micro output the micro instruction into MIR. Execute: MIR fields assert control signals currently for a single microcycle. Register transfers ALU operations, micro access. Sequence: micro program counter increments or branches using MIR branch address control condition fields, conditional branches, consult status low flags 0 carry negative completion. When microprogram signal return or reaches the final address, control returns to final fetch stage for the next machine instruction. The micro instruction often combine multiple micro operations in parallel, maximizing data path utilization despite the added micro fetch overhead. Micro instruction format and control signals. Micro instruction structure varies by implementation by common field included. Micro instruction fields F1, F2, F3, etc. Each field enables a group of stimulates micro operations. Example: source select mux, source mux select, destination enable, register enable, ALU function code. Encoding combines multiple control lines into compact fields. The next thing is conditional fields. Specifies which processor status flags or external condition influence branching. Zero flag, carry flag, interrupt request. And the next thing is branch field, BR, or sequencing. Determine next address logic, increment, unconditional jump, conditional jump, return from subroutine, useful to implementation loop, and multi-cycle memory operation. Next thing is address field, ADR. It provides an explicit next micro instruction address for jump or table driven sequence, can be absolute relative. Together these fields let a single micro instruction one perform many hardware action at once. Second, control the flow of the subsequent micro instruction, effectively making microcode a tiny specialized instruction set of control unit. Advantages and design trade-off. Flexibility and updatability. Microcode can be updated to fix error data. Add instruction to change semantic without altering silicon. Writable control stores enable fields, update and feature toggles. Simplified control design. Complex instructions are decomposed into readable microsequences, improving maintainability and erasing verification relative to dense hardwired logic. Instruction and set richness. Support complex CISC instruction and emulation layers. Microcode can be implement high-level construction or translation layer for backward compatibility. The final thing is performance and art cost. Microfetch overhead increases cycles per instruction versus optimized hardwired path. Control memory adds silicon area and introduces access time constants that must be balanced. Designers frequently use hardwired path for the fast critical operations and microcode for the complex or less frequent behaviors, achieving a balance between speed and flexibility. Real world application and impacts. In real world, as you can see in images, microprogramming has a shape practical CPU evolution. Historic and modern CISC processor, notably many Intel x86 implementation rely on the microcode to implement complex instruction semantics and compatibility layer. Firmware level microcode patches are issued to correct subtle CPU bugs or to harden behavior without physical calls. Microprogramming enables instruction set emulation. Processors can be implement software translators to run legacy binary efficiently. In educational setting and CPU prototypes, microprogrammed control simplifies experimentation. New instruction or behavior can be tested in mini-code before committing to hardware. Security note: microcode updates are powerful. Vendor distributes signal microcode to ensure authenticity and prevent malicious firmware modification. Conclusion and key takeaways. Microprogramming firmware for control. Transform control logic into readable, editable sequences of microoperation. It is a bridge between instruction set semantics and physical depth control. Choose microprogramming for flexibility, maintainability, and complex ISA. Choose Hardwired for minimal latency and maximal throughput. Hybrid exploits the best of both. Practical importance: microcode enables compatibility, fixed field fixes, and emulation. Understanding microprogram control unit is essential for the architects, firmware engineer, and design or maintaining modern processor. If you want, I can expand